Swayam Prabha. Digital India. Educated India.
The Sudha Gopalakrishnan Brain Center at IIT Madras is a multidisciplinary research and development center focused on brain research. Let's find out more about it from Professor Mohan Shankar.
This brain center is truly a unique cutting-edge research center that is imaging human brains at cellular resolution. And this is truly a frontier area because brain is something that we have really not understood well. In fact, we have very little understanding of the brain. In fact, if you look at how much we actually know about the brain, you'll be surprised to know that we actually have not seen the entire brain at cellular resolution, which is sort of the minimum requirement for you to understand an organ. And this is, an open-ended frontier research area. So IIT Madras about 2018 started, conceptualizing this center. The Office of Principal Scientific Advisor, Government of India, and Mr. Gopalakrishnan, who is our distinguished alumnus, a co-founder of Infosys, and a great friend of IIT Madras, all got together, said we'll set up something which is truly at the frontier of brain research. And that's how this center got started. And this center is truly multi and transdisciplinary. It involves technology, neuroscience, medicine, and when I say medicine, different fields of medicine. There are about 10 different specialties of medicine we work with. Then engineering. All of this is combined together to form this center, which you will see when you go around. We are taking whole human brains post-mortem and imaging them at cellular resolution. Now, what does that mean? So the brain has billions of neurons and hundreds of billions to trillion connections between those neurons. So we have actually not seen these neurons fully. And as you know, the brain is an evolving system, both anatomically as well as functionally, over a period of time, right from conception all the way to aging. So we are imaging human brains of different ages, genders, different backgrounds, diseases, normal, what we call neurotypical brains, and creating a large set of brain data which the entire world can use for decades to come. So this is a very complex pursuit, right? So you can quickly see the brain is a large organ, right? About 1.5 liters, a large adult brain. A fetal brain is somewhere around 100 cc to about 1/3 of a liter. And if you want to image this at cellular resolution, you have to have a large technology platform through which you can look at each cell in the brain. Right? And what we have done, and you will see this in the background, and you will see this in the lab, that we have built a very, very cutting edge, first in the world technology platform that can take in a human brain and section it at very, very thin slices of 10 to 20 microns, which is around 1/3 to 1/5 of the human hair, and process them, put them on a glass slide and image them at 0.5 micron so that you can see all these cells. Now, you can already imagine a human brain will have several thousands of such sections. So in order for you to do this in a high quality, scaled manner, it cannot be that it works for a few sections and then it doesn't work, then you lose that portion of the brain. So you need something which is truly automated, highly reliable and a high quality. So that's where the engineering and technology comes in. The neuroscience comes in after this data is generated, right? And we are targeting several applications. Right? Obviously, the first thing that comes to your mind is the medical applications, both developmental disorders of fetus and children, and aging and neurodegeneration, which is becoming a big problem in the world. India is starting to face that. Developed countries are already facing significant aging and neurodegeneration problems. These are the medical applications that we are addressing based on the understanding of the human brains that this data generates. So, when you go around the lab, you will see each step of what I just mentioned, which is acquiring a brain, postmortem brain, which is a highly sensitive and a time critical process. After the death, you have to acquire this brain within a certain hours, and the brain has to be preserved. Then the brain is frozen, and then it is sectioned into very thin slices in a very high quality manner, and then it is stained. There's a lot of physiochemical processes that it undergoes. Then we image them. Then once we image them, it moves into the digital domain. And now you're looking at not gigabytes and terabytes of data, you're looking at petabytes of data. Right? So that is, that's 1,000 laptops, right, of what you normally have. And this is one adult brain. So if you do hundreds of that, then you're looking at 100,000 laptops equivalent of data. And so we are building a huge computing platform, right, through which we can zoom in and compare different regions of the brains, both intra-brain as well as the same regions across ages and across development, and compare them, the neurotypical brains, which are what we call as normal brains, with the diseased brains. Right. So this is what will give us deep insights. Right. Of course, first of all, it generates new knowledge through which we understand the brain. Then we actually look for insights that will give us clues on how to diagnose early, how to treat these diseases. So this is a very large R&D enterprise, and we are really today globally visible. There are about 20-25 global collaborators from 4 different continents who are working with us, looking at this data and generating knowledge. Remember, this particular field went into dormancy for about 30-40 years. Right? And it is truly now at a frontier area where the leading R&D groups in neuroscience, the leading countries in science tech R&D are working on it. So this has really put India on the global map of brain mapping.